Okay, good morning. I'm extremely sorry that I didn't press the recording button yesterday. I'm really sorry. Sorry. So, but I will still upload my handout notes. Okay, so should be all right. And I will go through really quickly today to make sure that everyone can remember what I taught yesterday. So let's quickly, I will do quick recap for tomorrow because I forgot to press the recording button. I'm sorry for that. Now, I believe I start from this. The conclusion about this example is that if we have under if the motor under the same condition with the same power output and allowable stress of the shaft, we will, if we want to have more higher speed, we require smaller diameters. That's the conclusion of this example. And then we talk about statically indeterminate case for torsion. So you can see that it is really similar to chapter 2. We use equilibrium equation, compatibility equation, and then torsion angle of twist relationship. That's it. So everything is really similar to what we learned in chapter 2. So I guess this is okay as well. And strain energy as well is really similar. You can determine the strain energy stored by the torsion using torque or torsion. It's okay. Torsion or torque they are all the same. Torsion versus angle of twist diagram. You calculate the area under the line, which will be the triangle because we assume that linear elastic range. So everything is similar to chapter 2. And if you want to summon up together all the non-uniform, you need to summon up all the segment of the bar if the cross-section of the bar is non-prismatic. So you either do. Did I do something wrong? Okay. So total strain energy can be summoned up together by integration or summation. And then strain energy density is really similar to we learned in chapter 2 that the strain energy small u, strain energy density small u is stress, shear stress, and shear strain times together and divided by 2. Very similar to chapter 2 as well. And then this equation, this example, the conclusion of this example is that the strain energy cannot be superimpositioned, which means that if you have two multiple loading case, you cannot just summon a single of each of them. You need to calculate them together because they have couple term. And this one is really similar to what we learned before, and we use different method, different similar triangles to obtain the x, the function of the diameter of which is the function of x. Yes, and then we can determine the internal energy and strain energy. Strain energy stored by the torsion we gave, and because we only have one torsion, so we can obtain the rotation angle by using the U and W's work, right? So we can obtain that directly. Okay, so that's the chapter 3 recap. And chapter 4 recap is that we're going to learn the beam behavior, beam behavior subjected to lateral loads. What does that mean? Because the actual direction of the beam is that, so all the loading in the in the case we study in this chapter is they always perpendicular to the actual direction. And then the main purpose of this chapter 4 is that we're going to draw the shear force diagram and bending moment diagram. This is extremely important and basic because chapter 5 require the fundamental knowledge of chapter 4. Every problems in chapter 5 need to solve chapter 4 problem at first, and then you can proceed. Okay, so if you cannot you don't know how to solve problem in chapter 4, that will be really dangerous. You cannot get any score in chapter 5. So this is really important. Okay, so be aware. And then yesterday we introduced types of support. 3 types of support, really important. Triangle and circle and wall. 3. Okay, 3 types. Triangle. Triangle can provide 2 reaction forces, which means that it cannot go X direction and Y direction freely. Cannot, right? Cannot. So 2 reaction forces, RV, RH. But roller means that it's just like a train on the track. So you can go left or right freely, X direction freely. So there's no reaction force in X direction, but you cannot go off the track. So you cannot go up and down. So the support provide 1 reaction force in Y direction. And ultimately, you have fixed support as a like you're stuck in it at the wall. Okay, so you cannot go up and down and left and right, and also you cannot turn. So you cannot turn. So you will have the reaction moment. Okay, reaction moment to stop the rotation, stop the moment. Okay, so this is a really important 3 types of support. And then we focus on 3 types of load. The first one is point load. Point load is really simple. You can have P1, P2, P3, and P1 can or P can be the force can be in the uplift mode. Maybe you can have you can make it with the vertical component and the horizontal component, and it will determine the reaction force in X direction. Okay, and then of course the point load has the unit N, and distributed load is a little bit complicated because Q has the unit N divided by M. So the total effective load amount will be the Q times their length. Okay, so you can imagine the Q is kind of the height of the shape. The length will be the width of the shape. So the total effective load amount will be Q times C. Okay, in this case. Of course, in this case, still, it will be the area of the effective amount will be equal to the area of this shape. But we need to notice that the effective load will go through the centroid of the shape, but the trapezoid T-ing is really difficult for us to determine the centroid. So it will be better for us to make it 2 parts. The first part is rectangular, which we really similar. We're really familiar with that. Or triangle, we're very familiar with that as well. So this shape with the area Q1B will go through the rectangular centroid. But for the upper part, this is triangle. The triangle part, the value of the area is this one, and it will go through the centroid of that triangle. Okay, and when we do that, when we simplified the effective loads by when we simplify the distributed load to effective load, the purpose is that we are going to do the force balance. Only if we are going to do the force balance, we will make it effective load. Okay, otherwise it will be really difficult for us to do the moment or times the arm, forcing arm, right? So it's really difficult if we didn't use the effective load. 简单来讲，就是我们在做力平衡要去算这些反力的时候，我们会把就是那个分布载重变成等效力，等效力，这样我们才好去做那些什么 moment 啊的 force 啊的 balance。不然的话，你这个这个分布，你还要去那边一个一个去算它的那个利弊的话，这未免太困难了哈。So that's it. Then the final types. Okay, now this is new. Recap is finished. Okay, so types of loads. The third type is moment. The moment, okay, so basically M1. So M1 could be like this. Oh, sorry. Could be this one. Okay, M1. So it will rotate it. You can imagine that there's the bar. Okay, the bar. Imagine bar here, and you put your hand to rotate that, so you can bend this thing. Okay, so although it's really difficult to talk about example in real life, but I guess earthquake can provide such kind of bending for the thing. And also I shared a news, right, in our Facebook club yesterday. I found that they summarize all the cracks types in our walls or beams or something, right? So you can see that all the cracks, they either occurred at the corner, because the shape of the corner will cause the stress concentration, just like the remember the first day we give a bar like this, and then you can see the concentration load, right? This is stress concentration. So you can see the cracks will always occurred at the corner and also 45 degrees of the material, because the shear stress occurred, maximum shear stress occurred at 45 degrees. Okay, so which means that the mechanics material is really useful subject, useful course in our daily life. Okay, let's check if there's any cracks in our. It's okay. And also, did you notice that we have a there's a door, locked door. Did you see that? Locked door in the front of our building. And then did you see a lot of bricks fall down? You see the big cracks. Did you see that? No? Mm, mm, mm. I made a photo. Where is the cracks? I don't know if you can see that. How can you see that? This one? The door with the cracks like that, right? So which means that this is not the shear. This is not shear cost crack. Did you see that? 就我们的那个铁门啊，每次都关着的嘛。它如果你打开进去的话，它下面都是地震当天，就是这边都是，就是这叫什么？就是砖块都掉落了，然后它的门上面就有一个这样噔噔的裂痕。这个裂痕就不是 shear cost，right？ 因为它是直的，好，所以它就不是我们的，它就不是剪力破坏啊，它不是剪力破坏。那 对啊，所以就是还蛮特别的，所以就知道，它这不是解离破坏。那危不危险呢？我是不知道啦，我是不知道，反正还蛮恐怖的。嘿，好，anyway, so that's it. Let's continue our lecture. So types of loads. We have done the introduction for 3 types of loads. Now let's talk about reaction force. Okay, reaction force. I guess all of you understand that. So I just do really quick. Here you see the triangle, which means that it is hinge support. So you have two, well, I will move a bit because I wrote it, RA, all right, and HA, and because they has the P1 and P2. Okay, P2 and Q is this one. This is the distributed load Q. Okay, and then we can have a QC, all right, as a effective load. And of course, excuse me, this is, sorry, this is half C. Okay, so now you will have another reaction force on B, which is RB. Okay, and RB is a roller, so there's no XY direction, sorry, X direction reaction force. So reaction force, dun, dun, dun. Okay, 3 type of that. So now we are going to solve the HA and RA and RB. They are unknown, right? So we will starting to do the force balancing of P1, and the P1 can has two component, right? P1 can have 2 component, horizontal and vertical. So of course, Fx, sigma Fx equal to 0. So HA minus P1 cosine alpha to the left, right? P1 cosine alpha equal to 0. So HA equal to this one, no problem. This is for these two. Okay, and then sigma MB, sigma MA. If you do the sigma MB as a origin, you can see RA makes clockwise. Clockwise means negative. So minus RAL. L is the force arm, right? And P1 sine alpha, which is this one, was the counterclockwise, so it's positive, and their forcing arm will be L minus A, and P2 is also counterclockwise, so plus P2L minus B, and then please notice that this one is distributed load. So distributed load can be when we do the force balance, right? So the distributed load should become and regarded as a effective load, QC. The QC is at this part, so you can treat that as a point load, but this is the effective point load. It is counterclockwise, so positive QC times C over 2. So you have QC squared over 2. Okay, so careful about this moment is here. Okay, equal to 0, and then you can have RA equal to blah, 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 blah. And sigma MA, again, do exactly the same thing. So QC now is here. QC is going to do the clockwise, so this is minus, and minus QC times L minus, L minus C half. Okay, this is QC, has this one as a forcing up. The rest of it really similar to the previous one, so you can get RB. So notice that when we do the force balancing, we need to make the distributed load into effective load, effective point load. It will make your force balancing easier. OK， 听得懂哈？就是分布载重的在做力平衡的时候，请把它转变成等效的点力了哈 ，point load。那这样子的话，它是通过它的行星的，这样的话你在做这些力背的时候就会比较好算。OK， 就这样。Next one, shear force and bending moments. Sign convention, plus and minus. So let's take a look. Right. So in this course, we are going to introduce sign convention. I believe in different countries, they were using different sign convention. Really. I don't know. I have seen a pictures. Well, this is really difficult by using English, so I using Chinese. 就是那个，我看到一个迷因图啊，哈，就是他在讲说有猫，就是有胖的猫跟瘦的猫在一个椅子上，然后胖的猫跟瘦的猫，然后他就在下面画那个简历弯曲图哦。我真的有看过这个东西，在网络上，然后我想说，哇，这个迷因未免也太科学了吧？但是我后来发现，他那个迷因图的那个正负号跟我们的是相反的，真的哦，真的哦。所以也就是说，不同的国家会用不同的 sign convention，哦，这边要小心一点。So I just talk about when I saw the pictures, shear force diagrams in different country, they may use different sign convention. I have seen a completely opposite sign convention in other countries. So should be careful. You need to be careful. So I just introduced, we make this as rule, right? A system we use in this course. Okay, so be careful. Now I will give you an example to help you to understand the sign convention. So now we have a P here, and we have a fixing end in the, at the right hand side. But you see this is fixing end, so we will have 3 reaction force. But now, because we don't have a horizontal force, applied force, so we only have our RB, right? But we don't have the horizontal one because they are become 0, okay? But we do have an M1, okay? Or M and MB, okay, MB, right? So this is the case. So now we are going to draw, or we are going to determine at a point in that beam distant to the origin X, what is the shear and moment value at that point? They will change. The value of the shear and moment will change in different point at different X. Okay, so we just need to know that what kind of value in each point in that material. Okay, in that beam material. So as usual, if we want to see the force at that point, we just cut it, right? We just cut it. Okay, so when we cut it, we have 2 choices. The first choice is we leave the left-hand side. The other choice is leave right-hand side. But now, in this course, we will leave left-hand side. Okay? We are not leaving right-hand side. So the meme pictures I saw on the internet, their country choose to leave right-hand side. So that's the reason why their value are opposite to ours. Okay, I guess you can understand what I'm talking about. So now I cut it and I leave left-hand side. Okay, I'm not leaving right-hand side. Okay, so all the all the shear force diagram, moment diagram we plot later on is based on this. Okay, not based on that. We based on the part we left on the left-hand side. Okay, be careful. And then let's take a look. So if we left and left-hand side, we leave left-hand side, okay? And then it must have some force on that end. Otherwise, this member will fly away, right? So which means that it must have a force at this side to balance it. Otherwise, it will fly up to the top, right? So this is the shear force on that surface we cut. Okay, it must have some force on that. And also, you see, this is up, this is down. It will rotate like this, right? Dun, 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 dun. So it must, but it doesn't, right? So it must has a moment to cancel the rotation. So it maintain this part equilibrium, stay quiet in this place. Okay, so when we cut it, we naturally can draw first one, V downward and M upward. And then you see, because if we leave the right hand side, it must have a opposite V and opposite M. So that's the reason why other countries may have different side convention of our shear diagram and moment diagram. Okay, so again, I will. So you can imagine that. Dun, 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 dun. Okay, so we choose to leave left hand side. Okay, and we choose that. Okay, and we choose the left hand side. And the shear force. Okay, actually, these two blue dots are the same point. Okay, are the same points. We just cut it and imaginarily cut it and separate them. So shear force, we define. If the shear force rotate this one, I just help you to memorize it. If you this shear force rotate this point, in clockwise, it will be positive. So this is a little bit different from what we learned previously. So be careful, but there's no reason. We just choose that as a positive. Okay, so shear force. Clockwise. About the point is positive. Is positive. Okay? And moment is how to say that? Upward is positive. 好烂的英文哦 ，positive. I'm sorry. You can see that I previously using Mandarin to Chinese to write it, and now I need to translate it instantly. So really bad translation, but I hope you can understand what I'm talking about. 好，其实基本上就是我们要跟大家讲正负号。那正负号的话，我们要取的是左边。好，那我们左边呢，我们的只要因为左边我们画出来，如果是往下跟往上的话，我们的下就是正的 shear force 是正的 ，OK，shear force 是正。那我这边跟大家讲一个记的方法，然后就是说往下，然后它会绕这个材料点去转。它如果是 clockwise 的话，我们就视它为正。那 moment 如果它是对那个材料点朝上，让它变成微笑的话，它就是 positive， 它就是正。那你可能会觉得说，哎，老师这个 V 怎么往下，怎么会是正啊？哎，没有理由，原因纯粹就只是 sign convention， 就是正负号，我们就是这样子写的。那如果你硬要让这个 V 变成往上为正的话，那你就要取右边，那这样就会你的答案就会跟我们所有的人相反哦，那这样子就会蛮麻烦的。当然你如果这样做也是对的啦哈，但是就是你可能就会增加助教改的麻烦哦，所以其实我还是希望就大家都统一用左边的，然后反正不管怎么样，你一切下来你就把简历画往下。然后 m 往上，就是假设它的方向。那到时候如果是错了的，就是算出来是负的，就表示说你刚刚假设错了，但也没有关系。总之，你一切留左边，然后往下往下的简历，往上微笑的 m 的 moment， 这样哈，这就是这一章的 sign convention 的，就是的规则。如果你真的没办法理解的话，你把它背下来就好，没关系，它就只是一个规则而已，没有什么理由哦。I'm sorry. So it's just a rule that in this course, we will using the left-hand side. So when you do the cutting, imaginary cutting, we just cut and leave left-hand side, and then we write down downward as a shear force positive, and upward, make it smile, make this material smile, and it is positive moment. Okay, so again, we choose, if we use the right hand side, okay, so we will choose this and that. We will choose this and that. Okay, right hand, we leave left hand side, so our shear force and moment will be drawn on the right hand side of the element, right? So we will pick this, and then we also pick this, and pick that, and pick that. All right? Pick that. So you can see that to this one, to the downward, and rotate this material point clockwise. It is positive. And it rotate to the material point counterclockwise is minus. Okay, and smile curve positive m, a quiet curve negative curve. Okay, that's it. 好，这是比较需要大家就是接受的地方哦，就是哭哭曲线就是微笑曲线就是正的 moment， 哭哭曲线就是负的 moment， 然后简历是比较麻烦啊，简历就是右边往下的话为正，右边往上为负 好，这边就是跟这边有一点跟我们认知的一般的力假设方向有点不一样，这边要小心一点。All right, so I hope you can accept this, and then we can proceed our teaching. Any questions? Okay. Right. Thank you. So now let's continue. Find V and M, shear and moment. Shear and moment. V and M at a place that a small distance to the left of the midpoint of the beam. Midpoint of the beam. Okay, let's take a look. Here, there's a force on the at quarter of length, and N0 and 0 at the center of the beam. Now, the first question is that we want to know the V and M slightly to the left of the midpoint. Okay, the slightly to the left. So this is question number 1. And the second problem is a little to the right. A little to the right of the midpoint. Okay, although I did that a little bit exaggerate, right? But the 1 and 2 is actually slightly to the left and slightly to the right of the center. Okay, now before we are going to do that, we solve the problem, we need to see the reaction force. So triangle has two reaction force. This one is RA, and this is RAH. But all of us know that this is equal to 0 because there's no applied horizontal load. And RB is the roller, so they only have one reaction force. Okay, RB here. Now, only 2 unknowns, so we need to determine the reaction force first. Sigma MA equal to 0, so minus PL divided by 4. Why minus? Because P rotate about A in clockwise, right? Clockwise, so it's minus and minus M0. Oh, you see that M0 is clockwise, so it's minus. And you don't need to times the forcing on because this is the moment, okay? So no need to time force on, right? Because it itself, it is moment, so you just add it. And it rotates in clockwise, so it's minus, all right? And then next one, RBL. RB upward and rotate A about counterclockwise. It's plus. Okay, so equal to 0. That's it. This is the first one, and you can get RB equal to P divided by 4 plus N0 divided by L. Okay, so RB has been solved. Sigma MB equal to 0 is our next procedure, next step. RB minus RAL. Why minus? Because RA go upward, we assume that positive, right? So it upward become clockwise, so it's minus. And plus P times 3/4L, this is force arm, right? And force arm This one go downward to the B is counterclockwise. It's positive. And no, still minus M0 because this is clockwise, right? So it's minus MD and 0. So M0 and 0 for both origin A and B, they are all minus because NO is just the minus in the system. We applied equal to 0, and then we can get RA equal to 3 over 4 P minus N naught divided by L. Okay, so RA, RB, they are all solved. So we are ready for examine the V and M slightly to the left of the center point. So if we want to see the internal shear force and moment at that particular point, we just cut it, right? So we now cut here. And we will leave left-hand side, right? Left-hand side. We cannot, now in this chapter 4, we cannot leave right-hand side now because we are going to give a correct sign convention. Okay, so that's a little bit different from previous. So now, so you can see that I leave left-hand side. Okay, and if we leave left-hand side, we have P here, and we have RA here. So now, very important, because I cut it and leave left-hand side, and then we need to assume the V and M as a positive way, right? Positive V downward. So this is really important. And M. Okay, so be really careful about this. Okay, and of course, this V is this one. This M is this one. All right, so we are going to check this position. This position, what is the shear and moment value in this position? Okay, so now shear force. Shear force V sigma Fy equal to 0, so you can have Ra minus P minus V equal to 0. You see, this is really interesting. We say this is V is positive, right? But when we do the force balancing, it is downward, so it becomes minus. So did you see that it's a little bit confusing? Okay, so you see the reason why I said this is a little bit, you need to pay attention on it, because when we define the V is positive, but when you do the force balancing, it becomes negative. So this is really confusing, so because they are separate. Okay, so you need to be careful. 好，这边有没有发现一件事情？就是说，我说，哎，我们留左边，我们的 V 等下数字是正的，然后哇，它要朝下，对不对？但是我们在力平衡的时候，哎，因为它朝下，它变成负的，所以这两件事情是分开的。就是我们画 shear diagram 这件事情是向下为正，我们等下值会是正，但是我们在做力平衡的时候，还是一样照以前的 x、y，x 正方向是往右，y 方向正为朝上，所以这边要非常非常小心。两件事情是两码子事哦，画 shear diagram 跟力平衡是两码子事哦，所以这边有点要注意。好，这边是常常学长姐觉得怪怪的地方，会常常让你觉得很，哎，为什么一下正一下负？好，但是我们要把这件事情分开的话，你就会比较轻松一点啊。就是 shear diagram 是 shear diagram， 正负号是它那边的，但是我们在做 force diagram 讲错 force balance 的时候，你就跟之前一样哦，上为正，下为负，左为负，右为正。OK， 好，加油。Then we have V equal to minus P equal to P divided by 4 minus N no divided by L. Okay, so this value, this is the V value, okay? And then if we want to draw a shear force diagram, we will just draw this figure, draw this point, okay, at this value, all right? 我说啊，这个东西就是的 v 这个值就对了。这个值是多少？我们到时候在 shear diagram 的时候，我就画多少。它是正，我就画在正；它是负，就是画在负。那它如果是正的值的话，表示说它的剪切应力是朝下的。那如果它这个值是负的，它就表示说我的剪切力是朝上的。OK， 所以这边就只是纯粹值而已。好，这边就是值。Right. So moment m sigma n. Okay, I will give you a really blue dot here. Okay, blue dot here. It must be equal to 0, right? 0. So negative R A L divided by 2 and plus P L divided by 4 and C plus N. Okay, you see N here is counterclockwise, so it's positive. Okay, equal to 0, and then you can get N equal to PL divided by 8. Okay, minus N no divided by 2. Okay, so this is the result we obtained. All right. Okay, so this is a point slightly to the left of the center point. How about slightly to the right? So again, now we are cutting this line, okay? We pass the center point, so now N no appeared, okay? N no appeared. So P is still here, and N no is here, okay? And RA is still here, no problem. Okay, so you can see the difference. And then, okay? When you slightly pass the center point, and no occurred. And then, again, notice that because we cut it, we need to assume the V and M. V downward and upward. Okay, that's it. And then we will do exactly the same thing for the shear force balance and moment balance. And then I will give you a spoiler. Your M will be equal to PL divided by A plus and no 0. I will finish all the calculation, but this is really interesting. Just passing one point and then your moment will be different. So I will continue our lecture next week. Okay, just saying that they are really interesting. Different point has different moment. That's it. Okay, so if you have any questions, just come to here and I will explain to you. Thank you. See you next week. Hey, sorry. 觉得这是报给他自己做，还是他觉得你只是觉得他只好有东西。对啊，我就想要问这件事情，他其实是他不知道，然后那你有看他的图吗？不是，我说他不是有放图吗？他那个图跟你的那个答案是不是完全一样？这种感觉，因为哎，如果他不差多少，好像讲一怪怪的。但是我觉得他答案不可能跟我一样，因为自己 match，我觉得不跟我们对，所以你觉得？那其实跟刚在的时候也看到他的电脑在动，是不是？好，没关系，好，这个我就知道了，好，谢谢。那下次再开始。对对。OK，问题。等我一下哦，等我一下哦，Stop sharing。为什么我的哇啊哦找到了，嘿嘿嘿，好。